hope my screen is visible. So for this session, we'll be going over recurrent neural networks, which are an advanced form of neural network which work with sequential data more effectively than the previous introduced models. Let me just screen the screen size. So what is a recurrent neural network or an RNN? So RNN is a type of artificial neural network which is designed to process sequences of data. Right. So there is a set of hidden parameter weights that are updated in sequence for each input token or whatever element is part of the sequence. Right. Of course, sequential data is not really limited to text. We can also think of voice and weather, forecast, stock market as all other forms of sequential information. Right. The idea of sequential information is the word or elements that come afterwards are dependent on the elements that came before it. Right. So this is the basic idea of structure of neural network on the right side. On the left, we can see a architecture of a simple neural network or a simple feed-forward neural network, where we have the input layer, which are the inputs to our model. Hidden layer corresponds to the actual model, which hold weights that need to be trained for the model to learn the behavior that we are trying to uh, train for. Right. And finally, the Y section represents the output layer, which is the output class or output text. Right. However, in case of recurrent neural network, what we do is instead of having a simple sequence of input, hidden, and output layer, the hidden layer is recursively trained over it over a sequence of input data to update the weights. And then finally, after the entire input sequence has been processed, we go ahead and generate our responses. Right. So for example, we can look at this particular image to see the functioning of a recurrent neural network. We have X our input, H our hidden weights, and Y as our final output. Right. So the training, let's say, start at X t minus 1, which denotes time period t minus 1. It trains the hidden parameters H t minus 2, which leads to some output Y t minus 2 as well. Right. So that can be thought of as one step of processing. Then at xt minus time t minus 1, the weights are updated again, and we get an output y t minus 1. Right. The idea is that for a sequence of input, we get a sequence of outputs but the weights that are actually trained uh, the parameters that are trained remains constant, but the values change over time. Right. So the idea is that the base of the model, the actual parameters, they remain constant, only the weight part is updated. So there is no structural change in the model. So how do we train a basic recurrent neural network model? We'll be training our recurrent neural model using PyTorch. Right, I hope you've gotten a brief idea of how PyTorch works to the tutorial that was given. Right. So in order to train our model, we'll be first be importing the Torch library, which holds the required functions that we'll be using to train our model. Right. So the basic library that we are using is Torch. In Torch, there is another subclass, which is called the NN class or the neural network class, which holds a lot of functions and models that we'll be using for our implementation. Right. Another sublibrary that is available in Torch is called the Optim library, which has a plethora of optimizer functions available in it. Optimizer function, as you might know, calculate how much, how well the weights need to be updated based on the value change between the expected and the correct predicted value. Right. Pandas, as you have seen before, is a package used to handle data, specifically data in tabular form. And we'll use this to load our dataset that we are working with. NumPy again is another package that is used to handle textual data. We're not really using NumPy here, but because we have Torch already available, and Torch is superior to NumPy if you want to implement your code for most deep learning tasks. The next package we will be importing is the matplotlib package that allows us to plot graphs for our particular modeling process. The main graph that we are interested in is the graph of the loss function. where how our loss basically reduces as we train our model consistently. Right. The next package we are interested in is the train text split function, which is a part of sklearn model selection package. Right. This function allows us to split our data in a specific ratio and then changes a set of, let's say, 1,000 elements into, if we want a split of 20%, we'll just pass that we want a split of 80-20, and then we can have our data split into 800 samples for training and 200 samples for testing. Of course, the sampling is done randomly. Another package that we'll be using is label encoder. Label encoder, as you have seen multiple times, is used to convert the target classes, which are generally labeled in the form of text, to numerical representations. Right. And finally, the package the package we are using is stores or returns the data, which holds the packages, classes, data set, and data load. So in generally, when we train any deep learning model, what we want is to load our data into a dataset object. And that dataset object is then converted into data loader object, where we try to make sure that our data is passed to the model in an near infinite sequence, right? So it breaks the model into sets of epochs, and then those epochs are randomized over so that we do not run out of sequential importance data, right? So that is the general idea. That one thing you have to consider, that whenever you train a language model, right? Basically, any deep learning model, you want to pass your data using these particular data set and data loader packages for torch, so that you can pass sequential amount of data without running out of. Now, the first step for training any model would be, of course, to first load the data set. Here we are using the SMS dataset, where our task is to classify whether a particular SMS or a message is ham or spam, right? So it is whether it's a scam message or it's a ham message, right? And this particular this particular file is stored in a TSV file or a tab separated value file, right? We read this particular file using the command pd.read_csv, which reads all the separated value files, and we can even load tab separated value using the read_csv function by passing the parameter delimiter is equal to tab, right? This ensures that the model understands that the current file we are working with is not a CSV file, but a TSV file. We mentioned that there is no header, and then the names of the columns are label and text, right? So our data set has two columns. First column is named label, which is the target, and the second column is labeled text, which holds our training data. Right. So here you can see a sample of the data df by printing df.head. Right. df.head by default only prints the first 5 entries of the data. Right. Here you can see the first element is something like go until 0 point crazy ... available only, which is the correct message. Next message is okay la ... joining with, and so on. Again, a correct message. Spam, however, you can see free entry in a 2 weekly comp to win FA Cup final, and you can see here it is labeled as a spam. So we have our data which has textual information for the SMS and its target label, which is either ham or spam. Now, first thing we want to do is we want to pre-process our data, where we pre-process our data by first converting all the text into lowercase format by just using the string function text.lower, and then we apply the split function, which basically splits our data using white spaces, right? So for example, in our first sentence, let's say we have only this large sentence up to available, then we will split our input text based on the white space, right? So go would be our first token, until would be the second, Jurong would be third, point would be next, right? And so on, our data would be split using this preprocessed text function, right? Then this particular preprocessed text function is then applied to a column of a data frame using the apply method, right? As you can see here, we want to change the column, that is df text, right? We use df text.apply preprocessed text, and then this preprocessed text function is applied to each singular entry of the text link, right? So that for the text column, all the rows, we apply this preprocess function, right? Then we update the value of df as df of text and label. So we replace the original df.text, sorry, df text with the new df text, right? Then we apply instantiate the label encoder, right? And then we apply label encoder to the label section or label column, right? So just to reiterate, to the label column, we apply label encoder where we convert our target classes to 0 or 1 since we only have two classes, right? To the text column, we first convert all the text to lowercase, then we split the text based on white spaces to tokenize it, and then we apply, then we replace this lowercase and tokenized value in place of the original text column, right? Here you can see when we print df of text, we get that our function is written like this: go until Jurong point. As you can see, point comma is a whole token itself, right? Similarly, crazy dot dot is a whole token by itself, right? Because you can see here in the actual text, it's crazy dot dot and then space, right? This is the entire token uh, preceded and forwarded by a sprite space, right? So that is how the splitting will happen. Of course, this is not the best way of creating tokens, but since we are only working with like giving an example, we are not really going for that hard into removing punctuations and everything, since we have the resources to handle these kinds of cases as well. So here we can see we have a total of 5,071 as the last entry. So we have a total of 5,572 entries, or 5,572 is the total amount of training data that we have. Right. For the next, we can print the label, and here you can see again 5,572 values. The values are either 0 or 1 corresponding to the classes ham or spam. Then the next step is to generate train and test set. The idea is to split the training data, which is a total of 5,572 samples, into training set and testing set. Here we pass the parameters df, which is the name of our complete data set. We pass the parameter test size, which corresponds to the how much split we want between the training data and the test data. By providing test data, the remaining value would go towards the training data. So we can see that 80% of the data would be used for training the model, and 20% of the data would be used for testing the model. This random state is used to signify that basically it is used for consistency of output. Whenever we apply train test split, it will always randomize the samples, in which case when you try to apply the same method again and again, you would get this different number of samples in training data and test data. The number of samples would remain same, but the actual samples would be shifted, right? So in that case, to get a consistent output on multiple iterations of the same command, we set a random state. Here we applied the random state of 42, so that whenever we run this code, we will get the same test split, and consequently, we will get the same outputs. Then we set our vocabulary. Of course, we can use encoder functions as well, but here we have just used two dictionary functions to create two set of uh, basically indexings, right? First one is the indexing for vocab, which is basically set of words or for phrase in df.text, right? So each unique word that is present in the entire df.text column, right? And then the word to idx, sorry, is a dictionary that has its key as the actual word and the value as the ID, right? And similarly, we can use this to encode our data, right? So basically, this particular text would be converted into the ID for go, ID for until, ID for Jurong, ID for point, and so on, right? So we are basically converting a textual expression into its corresponding numerical representation, right? Now that we have applied this train test split function, we can apply the encoding as well and convert our textual instances into numerical IDs, right? Here we can check the shape of both the train data and the test data, and we see that we have achieved the 80%, 80-20 split. We have 44, 57 examples in the training data and 11, 15 examples in the test set. Now, in order to train our model, we have to ensure that the samples that go to the model at one time sequence for processing are of equal length, right? This operation is called padding, where we try to make sure that all the input samples are of equal length, right? So they have equal number of tokens available, right? So what we try to do, we find the max length for the particular sequence, right? And then for the multiple max length sequence, if our particular sample that we are working with has less element than the max length, we pad the missing elements with the value or token value of 0. Right. So let's say 0 is our padding token. We have initialized 0 as our padding token. So here you can see max length is the max amount of length for any sample. Let's say the longest sample in our training data was of 80 tokens. We encountered a sample that only has, let's say, 15 tokens. So our 15 token sample that we have encountered now will be converted into a sample that is of 80 length, where the first 50 tokens would be the actual input or sample itself, and the rest of the 65 tokens would be just a sequence of this 0 token. Right, I hope that part is clear. We are just making sure that all the input samples are of equal length. Now we can print the, let's say, uh, the first element of the text column and the second element of the text column. And here we see that both the samples, although you can see that both have different sizes, right? Both have a different number of tokens in it, but they have both been converted into token length of same size, which is 171, which is also equal to the max length sequence that is available in the data. Right, hope that part is clear. Then finally, what we are trying to do, we are trying to convert this data frame that we have processed into actual dataset object. And this dataset object would be used to load a dataset and convert it into the format that will be used that has all the necessary operations available for PyTorch to process it. Right, because DF by itself or a Pandas data frame by itself does not have all the methods and compatibilities required to run a PyTorch code. Right. So how do we define it? We define a class called sentiment dataset. Of course, you can have the class name by anything. We are working with a sentiment classification task, right? Or we are working with a classification task. We are going with dataset, sentiment dataset name, right? And this particular sentiment dataset inherits or is a subclass of the main class dataset that we have imported initially from the package torch.utils.data. From torch.utils.data, we imported the class dataset and we use this class dataset to create our own class sentiment dataset. First, we initialize it as I think Arpan mentioned in the class as well. We first need to initialize our particular class where we will define the variables that we will be using for our particular operation. What are the two variables that we are interested in for our dataset? First variable is text, which will hold the column text from our dataset. The second variable we will be making is called labels, which will hold the column labels from the dataset. Len is another helper function that we are generating. This len will return the length of the text part. So how many texts there are in the particular dataset. Right. And similarly, in order to access the data, we need another function, which is the get item function, which will, based on the ID of a particular sample, return the actual text and labels corresponding to that sample. So we'll just use the get item function and then pass a particular ID or index for that particular data set, and we will get the corresponding value in the data set. Right, so these are the elements or the functions that are required. First one is initialization, where we declare all the variables that we are using. Second one is the length, which is a helper function, not necessary, but very useful. And then the third one is get item function, which is of course necessary because this is how you will be extracting or getting the data that you will use for actually training your model. Right. Now that we have built our sentiment dataset class, right? We'll use this sentiment database class to actually create an object for that class. So using the train data, we'll use the sentiment dataset class to set up our train dataset. Then we will again use the sentiment dataset class on the test data to create our test dataset. And both of these train dataset and test dataset are now compatible with the PyTorch functioning. So we can use them for training our model. Now, since we'll be using data loader for our actual training, which pass our data, our data into a model in a form of an infinite sequence idea, right? So we'll just convert our data set into data loader object by passing the actual data set, the batch size that we want to operate on, and then define whether we want shuffle or not. For training, we want shuffle. For testing, we do not want shuffle. We could have used shuffle for board time or uh, board time for test as well. However, we are not going to use it because we might need to compare the results with some other function as well. Right. Shuffling for training is quite of standard, right? Because we want to make sure that once let's say the training data had 10,000 examples, and we have seen all the 10,000 examples, the 10,001 example is not equal to the first example itself, right? So we get the data in a more of a shuffle fashion so that the model does not learn pattern that are corresponding to the sequence of the data. Like they want to learn from the data itself. Now, finally, after all the operations of the data, the cleaning part, the pre-processing part, and finally converting the data into some format that can be actually used by the PyTorch model, right? We will now build the actual model that we'll be using to uh, train on the classifier. So train on the data for our classifier, right? So what is the first name of the class? The name of the class, let's say, is sentiment RNN. Now we are using nn.module as our higher class, right? So we are importing from the class nn.module for all the packages that are required to train a RNN, right? So the idea is that if you are making your own dataset class, you will be importing from the dataset, which is available in torch.utils.data. If you're training your own model, right, you will be importing it from the nn.modules class. Right. Again, you can see for any class, the first function is init. Right. For this particular sentiment RNN or our classifier model, right, we'll be using first parameter, which is the vocab size. Of course, vocab size we have already calculated. Embedding size, which is the amount of vector, the size of the vector we have used to represent our embedding layer for word embeddings. Right, hidden size is the number of parameters that are available in the hidden layer of the RNN. And then finally, output size is the number of how many outputs that we are trying to project. Right, I hope this part is clear. Vocab size corresponds to the how many entries there are in the vocabulary or how many unique tokens there are available in our data. Embedding size is the number of uh, basically the size of the vector that we want to use for our word embeddings. Hidden size is the number of parameters that are available in the hidden layers of the recurrent neural network, and output size corresponds to the number of output class. Right. So as you can see, vocab size would be the length of our vocab. So vocab we have defined as a yeah. Here we defined our vocab as a set of all the unique words in our data. Right. So now that we have a set of all the unique words, we can just count on it. Right. Because the counting starts from 0, we will add 1 to get our vocab size. Right. Embedding size, let's say we want to use only 128 dimension vectors to represent each of these unique vocabulary word. The hidden size, let's say we have also decided that the number of hidden layers, sorry, the size of the hidden layer would be 128 parameters. Right. And finally, since we have only two classes, spam or ham, we have set our output sizes too. Now, what we need to do is based on the input, project an output. Right? That is how the model works. Based on the input, it gives an output, and that is done by the forward function. The idea of forward function is it will take an input, which is X. It will pass that input to the embedding layer, which is the first layer of a neural network. Then what it will do it will apply what do you call it? Transformation on it. It's not very necessary, but the main idea here is it converts it to x dot device. So when you are using GPUs, for example, you will set your device as the GPU or CPU, right? And basically using this to x dot device, you can forward a particular parameter from your CPU memory to the GPU memory for much faster execution, right? This is it. Now the output here would be RNN based on RNN H of 0, right? And then the output would be self of FC layer, which is the final layer output. And this is the shape of the layer. Okay, I think I forgot to go over this particular one. There are three particular components of our RNN that we are training. First is the embedding layer. Embedding layer converts our input text into the word embeddings. So its size should be the size of the vocabulary cross the size of the embedding layer, right? The second layer converts this particular output from the embedding layer, which should be the size of the embedding size, and then converts it to the size of the RNN, which is the hidden size, right? So it converts, it takes an input of the dimension hidden size, which is the output of the previous layer, and then passes it to the actual hidden layers of the neural network, right? And then finally, we have a FC layer, which is a final layer that converts the output from the recurrent neural network into the exact number of output layers, right? So if since we have an output size of 2, right, will convert the from hidden size to output size. So basically you can think of three components. The first component is embedding, which is converts the input, converts from the input, which is in natural language or indexes for the natural language, and then convert it into the size of word embedding. So it is vocab size times embed size. Then the second layer takes the embed size in input and converts it into the hidden size input for the recurrent neural network. And then finally, after processing the input layer, sorry, processing the hidden layer, right, the output from the RNN in this then passed to the final feed forward or forward layer, which is a single linear layer or dense layer that converts the model output from the original hidden size to the output size. Right, I hope that part is clear, but this is pretty much the entire working of RNN. You take an input, you convert it into word embeddings, you apply the RNN, and then finally the output of RNN is converted into whatever size output we want, right? We have only 2 classes, that therefore we have output size of 1. If we had 10 classes, we would have an output size of 10. Then we instantiate our criteria, which is our loss that we'll be working with. Since we are working with classification, we are going for the cross entropy loss, right? Then we'll decide an optimizer, which is Atom. We are going with one of the standard optimizers. You can try with other, like from my experience, Atom works more than good enough, right? We pass all the model parameters into this particular model, and the model parameters you can obviously guess are these embed size times hidden size times 2, right? So 128 cross 128 cross 2 would be the number of parameters that we have for this small model. Right, so all of these model parameters are passed into the optimizer because these weights need to be updated when we are doing the optimization step, or basically applying the updates for the optimization. Then we apply the learning rate. We have set the learning rate as 0.001. Again, this is another hyperparameter that you decide for your own, depending on your results. You do not want the learning rate to be too low, because then the model learns very slowly. If it is too high, the model may learn like the model might skip the information and actually go out of the learning. Basically, the loss instead of converging might diverge. That is the issue with having a too high learning rate. So what we want to optimize the learning rate, but since it depends on each problem itself, it is generally a hyperparameter that you set up based on certain preferences for each of the model that you are working with. The number of epochs we have set as 10. Epochs refers to how many times the entire training data has been seen by the model. So one epoch means that our entire training data, we have the training data size as 4457. So if our model trains for one epoch, it means that we have uh, worked with 4457 samples, right? So 10 epochs means these 4457 samples have been explored 10 times, right? And the model weights have been updated on that. Now we are interested in how the model trains or how the loss of the model responses reduces. So what we'll do, we'll create a list of the losses of the model and then keep track of the value of the losses after each epoch. Right, how we do it, we just append the current epoch loss into the losses list. So here our training starts for more epoch in range, number of epochs. So epoch in range from 0 to 9. We train the model, which is a predefined function in PyTorch. Right. Epoch loss currently, let's say we have not started any training, the current loss is 0. Then for text comma label in train loader, here we have defined our data loaders. And since we are working with training, we will load the train loader only. Right. Outputs is equal to model.text. You can apply model directly to any textual information and then get the corresponding output. This output of the model is the predicted output. Right. This is what the model thinks the output should be. Labels, however, correspond to the actual output. And we will now apply our criteria, which is our loss function, on the predicted output versus the expected output or the correct output. And this function will give us our loss value. The less the loss, the better the model. The higher the loss, the worse the model. Right. Then we set the optimizer values to 0 grade, another PyTorch special nomenclature. Right. Then you apply loss dart backwards to apply the gradient descent back, sorry, derivative backwards from the output classification back to the input, right? Through the neural network, then we apply optimizer the step to update the parameters of the model, right? Then we have epoch loss is equal to loss dot item. So we have in loss this loss here, we have our loss value, and this epoch loss is then added to the losses function. Sorry, losses list, right? But it is only added to the losses list after aggregating over the number of len of the train load. Right. Then we print the epoch number followed by the loss for that particular epoch. This is syntax for how to print a graph. We are printing a graph of the size 10,6. Right. We are plotting in a range from 1 to the number of epochs plus 1. So a number of epochs 10. We have a range of 11, I believe. Yeah. Up to 11. No, up to 10 only. 1 to 11. So the final number would be 10. We are trying to plot the losses, and the marker would be point object, right? So this O refers to this particular point for each of the epoch. The epoch 2, this is the point, epoch 3, this is the point, right? So this E marker equal to 0 corresponds to a point on the graph. Losses obviously corresponds to the Y label. This particular entire range 1 num epochs plus 1, this corresponds to the X label, right? So we take the figure. This is the size of the graph, 10 across the x-axis, 6 across the y-axis. We label the x dimension of the graph as epoch, we label the y dimension of the graph as loss, and then we put the title of the graph as training loss. These are the values. Here you can see initially the loss value was 0.40, then it went to 0.39. It stayed on 39 for a long time and it's still on 3. Right. You can see here the actual reduction in loss is minimal over multiple training steps. This is actually the graph of the training loss. It started at 402. Like maybe this graph might make it seem like there is a very gigantic reduction in the amount of loss. So as you can see here, the actual reduction in the amount of loss is minimal, right? So point from 403 to 395, which is a very minute amount and not really anything much negotiable, right? But This gives an idea that the amount of loss is reducing. And if we had trained the model for a lot more steps, right, or maybe would have used a more complex neural network model, we would have uh, reached a much better performance. However, even this model that has a very little reduction in the loss gives us an accuracy rating of 86%. Right. The idea is that even though the model weights were random, even when it was guessing for the first time, it was already giving very good results. That is why, even with a minimal amount of loss reduction, it has still reached a good accuracy rate. And how do we calculate accuracy? The model function that is defined in PyTorch itself. Say, where is the model? The model is defined as sentiment RNN, which is derived from NN.module. Right. So these are all the operations that are already defined in NN.module. We can already directly call model.eval, and this model.eval will give the evaluation. Right. Let's say we are going for a total of the test set size. The test set size is 1115 samples, 1115 samples. Out of those samples, we have already currently gone through 0 samples, and out of those 0 samples, 0 are correct, right? Then we apply torch.nodeget because we are also going over the model forward layer. We do not want to update the models, right? If we wanted to update the models, we would have gone directly with this particular steps, right? Where we're trying to update. But since we are not trying to update the model while this processing, we will set torch.node. For text and label in test loader, output equal to model.text, predicted torch.max output.data, 1, total is equal to label size. So we are updating total. Whenever we see a new sample, we'll update correct if predicted is equal to, sorry, the predicted label is equal to the correct label, right? And then we sum all of them, and the accuracy is 100 times the correct of divided by total, and we get accuracy of 86%. We can see that our model gives 86% accuracy, a bare bones model, right? Which has only 128 parameters for the embedding layer and 128 parameters for the hidden layer. However, it still performs well. Right? So that is the general idea of RNN. We try to update the models. As you can see, even though the input was changing for each training step, the weights that were being updated were the same hidden layer and embedding layer weights. Right? That is the general idea of recurrent neural networks. If you guys have any other questions regarding neural networks, you can go ahead and ask. Otherwise, Shikhan, you will start with the tutorial for transformers. Okay, if you have no more questions, I guess I can give it over to Shikhan sir. Wherever Hello everyone, am I audible?
Yes, yes.
Yeah, so Ashish sir will be holding a discussion session now. Right, we'll wait for 15 minutes and then Ashish sir will be talking with you guys to decide like get what your goals for this course, and if there are anything that particular you are interested in working together, you can go ahead and discuss that with sir as well. I hope you will wait. The session that was scheduled for today will take tomorrow, right? But for today, we'll be focusing more on the discussion with any specific interest that you have. Uh, if you guys have any interest, please feel free to let us know.